Well, if we want to take a synthetic approach, then we would follow perhaps Hilbert. But if we want to take a analytic approach, we could follow Birkhoff's axioms. Now, in a purely analytic approach to geometry, what we do is we assume we know all of the properties of the real numbers. Okay? And what we will do then is use those properties to help us know a lot of things about geometry. So basically what we're going to do is we're going to assume that there's a distance function that's going to be able to measure the distance between 2 points. Some of an actual underlying assumption here is the distance between any 2 points A, B is a non-negative real number, D, such that the distance from A to B is the same as the distance from B to A. That's not really made explicit below, but it's assumed below. But we could include that with postulate 1 if we wanted to. And we do talk about an angle sort of being formed by real numbers, and that there is an angle measure associated with that, and we could kind of throw that in with postulate number 3. Okay? But we have a line as a set of points, and a point and line then basically are our undefined terms. So what postulates do we have here? Well, basically we just have 4 postulates. The postulate of line measure that says points A and B, and however many points we have of any line, can be put into one-to-one correspondence, we'll call that function x, with the real numbers, so that the x of B minus the x of A, you can think of it as the x coordinate of B minus the x coordinate of A, so it's a coordinate function. So the absolute value of that distance of those two functions values, those two coordinates, is the distance from A to B for all points A and B. And we're going to actually assume a postulate like this in our treatment as well. So we're going to kind of borrow from this analytic approach. The point line postulate is exactly like one of Hilbert's postulates. One and only one line L contains any 2 distinct points P and Q. So that's nothing new. That actually is a regular postulate from the synthetic approach. And then we have a postulate of angle measure. We'll talk more about angle measure next week. But postulate of angle measure says that the half lines, or we'll usually call them rays, L, M, and M through any point O can be put into one-to-one correspondence A with the real numbers mod 2 pi, so that if A, B are points other than O of L and M respectively, the difference AM minus AL mod 2 pi of the numbers associated with lines L and M is the measure of that angle. So we assume that we can measure an angle, and that this is something that can be basically done between 0 and 2 pi. A postulate of similarity is postulate 4. If in 2 triangles ABC and A prime B prime C prime for some constant, positive constant K, the distance from A prime to B prime is K times the distance from A to B, and the distance from A prime to C prime is K times the distance from A to C, and the measure of angle B prime A prime C prime is basically the measure of plus or minus BAC, or plus or minus the measure of BAC. Then we also must have the distance from B prime to C prime is K times the distance from B to C, and the measures of those remaining corresponding angles must be congruent. So in other words, we have similar triangles. This is actually a, let me think about this one. It's BA and AC. So this is actually what's called a side angle side similarity condition that we're going to talk about later. So in Birkhoff's approach, you assume that up front, and then from that, if you have that, then it turns out you can get Euclidean geometry out of just these 4 postulates. But you do have to rely very heavily on lots of properties of real numbers, and you prove everything up using properties of real numbers. It has a certain advantage there. So then we can go in and define things like between, which were left as undefined terms in Hilbert's approach. For example, if A, B, and C are distinct points, we say that B is between points A and C. We notate that A dash B dash C if and only if the distance from A to B plus the distance to B to C is the distance from A to C. That's the actual definition we're going to take in this class. So we'll actually define between rather than leave it as an undefined term. And then we will also follow Birkhoff here. A line segment, the points A and C together with all the points B between A and C form the line segment AC. So that's a definition there. A half line, we'll call it a ray. M prime with endpoint O is defined by 2 points O and A in line M, where A is not O, as a set of points A prime of M such that O is not between A and A prime. We're going to define it equivalent way, but very similar. Parallel, two distinct lines have no points in common. They are parallel. A line is always regarded to be parallel to itself. First of all, notice that we're assuming that everything's in a plane here, so this is really postulates for a single plane Euclidean geometry. So they don't talk about skew lines, they're just talking about parallel only. A line is regarded as parallel to itself. That's a little bit non-standard, but it does have certain advantages. For one thing, it makes a set of parallel lines, it makes the relation is parallel to an equivalence relation. Okay, so if you allow if you don't have that lines parallel to itself, you lose the reflexive part, so you can no longer say it's an equivalence relation. So I'm pretty sure that's why he makes that distinction, although most of the time we will say, we'll not use that. We'll usually say a line's not parallel to itself. Okay, two half lines rays, M and N, through O are said to form a straight angle if the measure of that angle is pi. They form a right angle if the measure is plus or minus pi over 2, in which case we say they're perpendicular. So notice here we're doing these things strictly in terms of their measurements. If A, B, and C are three distinct points, the three segments A, B, B, C, and CA are said to form a triangle with sides of those segments and vertices A, B, and C. And A, B, and C are collinear, then we still call it a triangle, but we call it a degenerate triangle, which is really just a line segment. And we define any two geometric figures to be similar if there exists a one-to-one correspondence between the points of the two figures such that all corresponding distances are in proportion and the corresponding angles have equal measure, except perhaps for their sign. And two geometric figures are congruent if they are similar with a constant of proportionality 1. So they're building things up, congruence in terms of this similarity postulate. So it gives you a transformation there to base things on. So this is a purely analytic approach would go this way. So in the next one, we're going to see how that we're going to do it. And when it gets to the basic setup for most of the things we're going to do synthetically, but when it gets to this idea of measuring lines and also angles, and then also doing some of these concepts like between and line segment and ray and so forth, we are going to go ahead and use the analytic approach at that point. Okay, and I'll show you how we're going to be doing that for our class in the next video.